Hello and welcome to a new problem solving session, and we have a new problem at hand, and we can start reading the statement of the problem that says 2 point charges with masses m and capital M. You can identify them here and here. And identical positive charges q are located at a distance L from each other in a uniform electric field E directed from M to M, and at the initial moment the velocity of the points are equal to 0. Find the maximum distance between the points during their further motion, afterward motion, considering that the points are always moving along the same straight line. So we need to solve them. And we can start with Newton's second law of motion, because I can see here this charge q has been acted upon by two forces. One is due to external electric field E, and that is QE, and another force due to this point charge q having capital mass capital M in this direction, and this force can be written as kq square by suppose that at any arbitrary moment the distance between them has become simply equal to r, so this force will become kq square by r square. I thought r is the distance between two charged particles at a later moment, sometime after the start of the motion. And you can see this force, this charged particle is also acted upon by two forces. Both this time are in same direction. One force is QE, the force by external electric field, and another one by this charge Q here, and this is again kq square by r square, if r is the distance between them at this moment. So we can write their accelerations. So I'm going to write the acceleration of point mass m, a small m, at this moment, and E1 can be written as simply as minus y minus, you can identify yourself, divided by m r square, force by mass, plus QE by m, due to this acceleration is imparted by the external electric field, and write down this equation 1. And in the similar manner we can define the acceleration of point mass capital M here, and write down this acceleration A2, and it will be of course kq square by r square capital M plus QE upon capital M. So we have the accelerations now. Let us now find the relative acceleration of the points, because it is going to provide a new angle to think on this problem. And I have worked with problems like this, so I have an experience. And if you can find out the relative acceleration simply by A2 minus A1, so A1 is at rest or something, you have put your observer at a small mass m, you can find the relative acceleration and you will get something good equation, like an expression, a very good expression for this, and this will be kq square by r square, m plus m divided by mm minus QE, m minus m upon mm. And I have deliberately put a minus sign here, so that I will be able to write down something else. I can think like I have a fixed point charge Q here, and there is another point charge Q here at a distance r from it, and this one is fixed and this can move, and there is also an external electric field E1 in this direction. This one is fixed and this one is moving, and at a distance r, all from the basis of this equation. If you closely watch this equation, this same equation describes the motion of a point charge q with mass mu, and mu is nothing but m divided by m plus m. This is sometimes called reduced mass, and it is moving in the field of a stationary point charge q that you can see here, and in a uniform electric field this E1 in this direction, and this E1 has got a magnitude equal to E m minus m by m plus m. How? Because its acceleration here, this charge particle's acceleration here is given by this. Acceleration is given by, if you can see this, acceleration is given by q e m minus m by m m, and if we can think that this is provided by an external electric field E1 to this charge q, you can write it q E1 upon mu. Mu is its mass. So if you can write here, if the value of E1, E m minus m divided by m plus m, and now we need to divide by mu, and mu is something here you can see. So it's better to multiply it by m plus m by mm, and you can see the rest of the things. This is it. And why in opposite direction? Because it has come here with a minus sign here. So we have a new problem at hand. And what is this new problem? New problem is we have a fixed charge q and a moving charge q at a distance r from it, both of equal sign, and this charge q is also moving in an external electric field even, and this is fixed, so we don't have to worry much about this charge q. This is fixed. This can be acted about other forces rather than q and E1, and this is now fixed, so we don't need to worry about. And let us consider this equivalent problem other than we were solving earlier. So now its potential energy you can write here as u or phi. Potential energy is u, all right. U is workable, and u as kq square by r plus negative work done by this external electric field, and this is simply q E1 r. As this is charge multiplied by electric potential and a uniform electric field, you can get this electric potential here. So you can write it as q E1 r simply. This is quite simple. This is writing like mgh, and this is mgh. mg is q1 and h is r, and q E1 is a constant here, so no problem writing this. And if you like to draw a diagram of this potential energy versus this distance r, you can draw it easily. All of you, I guess, is very much familiar of drawing such graphs. I'm also trying to draw u versus f r graph, and this graph will specify many things. The first term is kq square by r, that is kq square is a constant, and it's multiplied by 1 by r. So u for this expression varying as 1 by r, that is a rectangular hyperbola like this, and another one u varies along directly proportional to r. So the graph will be something like this. Slope having QE, y equals mx it is, and so these two have formed, this two has formed two asymptotes, and the main graph will be lying between the two, simply something like that. So this is the main graph, u versus r graph. You can draw it if you know how to draw the graphs. And from this graph you can see, you can find the path of motion of charges, or at least you can find the position of charges between which the charge particle is bound to move. And if the maximum potential energy is u naught, if the maximum potential energy unit u naught, the charge particle is going to move between these 2 points. Call this R1 or L1, L2, and there is a bottom somewhere here. Yeah, bottom, the minimum, local minima, and call this point L0. So the charge is bound to move between L1 and L2 because there is the maximum potential energy. And charge particles or any particle move in a conservative field between these 2 points L1 and L2, and these are their potential boundaries, we know it. So they should have here they have their kinetic energy is minimum, that was 0 initially, and so they are going to move in between them, L1 and L2. And yeah, so you can write this equation ur as simply in terms of u naught as u naught equals kq square by r, yeah, plus q e1 r, like this. Oh God. Though for u naught you should write L1 here, and but I've just put u naught here, and so u naught is the boundary, the maximum value of potential energy. And if you like to solve the equation in terms of r, or you can find du naught by dr or du simply, just forget this u naught for a moment, and if you calculate du upon dr equal to 0, you will get the value of r, and what it may be. The value of r will be under root kq by e1, and this is our L naught basically in this picture. And this picture simplifies everything. That means if the length, initial length between the two charged particles, this L thing, is less than L naught, the maximum distance between the charged particle is going to be L1, which is initial length, because charges has the system of charges has total mechanical energy simply as at the initial moment, because there were no kinetic energy present at the initial moment. So, and this energy is purely potential. So the maximum distance between the charged particle will be the initial length, whatever the length is. But if this length L is less than L naught, then also the distance between both charged particles will be the maximum distance between the charged particle will be initial length. And if the initial length was greater than L naught, and in this case also the maximum distance between the charges is equal to the initial length. So what will be the maximum distance between charged particle during the whole course of motion is the initial distance in all cases, whether it is less than L naught, greater than L naught, initial length, whether the initial length is less than L naught or greater than L naught or even equal to L naught. In the case of L naught, the distance between the charges is not going to change, and in both the cases the maximum distance between the charged particle is the initial length, whatever the initial length is. So this problem is kind of solved, and this is also a method to solve such kind of problems. Thank you very much for watching.